Now to understand the reactions of the carboxylic acid derivatives, we're going to see a couple of mechanisms that we will see in several of those reactions. So two central mechanisms. We're going to see one mechanism under basic condition and one under acidic condition. Now I'm going to get, for example, the acid chloride. And typically these two, the chlorides and the anhydrides, which are more reactive than these two, they will go more to the mechanism under basic conditions. Under basic conditions, remember that essentially the species will have either negative charge or neutral. No, you don't propose a species with positive charge under basic conditions. So if this is the acid chloride, the acetyl chloride, for example, we will have a nucleophile, say that we're going to look into examples, but a strong nucleophile, for example, with a negative charge, the mechanism under basic condition involves a first step, so say step 1, nucleophilic attack. And this is what I have here in this arrow. That would lead to the formation of a tetrahedral intermediate. So this tetrahedral intermediate. And then we have another step. So step 2 is a loss of a leaving group. And how this is happening? Well, now we said already that chloride is an excellent leaving group, so we're going to reform the carbonyl group, and this will depart. The end result, we have, again, the carbonyl, and we will have the substitution. So these reactions, remember, are nucleophilic substitution. You're going to be replacing this by what is a nucleophile. So that is the mechanism under basic conditions. And now I'm going to erase this, so just leave the example of the acid chlorides. Or I'm going to do another example, a little different. So that's the mechanism under basic condition. I'm going to do the mechanism under acidic conditions. So say now that I want to do work with an ester. We know that esters are less reactive. And typically, we need the acid catalysis for those derivatives that are less reactive. So it can happen with, I'm going to change the color, with esters, for example. So say that I have this, and I'm going to do what nucleophile? We can do the hydrolysis of an ester, for example. And under acidic conditions, I will have, let's do explicitly instead of driving H3O+, I'm going to draw my hydronium here. And so the first step will be protonation at the carbonyl. So you will form, so step 1, let me just separate this. Under acidic condition, step 1, I'm going to write it over here. So this is this, right? Step 1, proton transfer. So I get that. The result of that will be, now I'm going to have OH plus, and here OR. That is the result after the protonation. Okay, so let me do this. Do it again. Okay. Now, in the second step, we will have a nucleophilic attack. And now I'm using a nucleophile that's actually neutral, not as a strong nucleophile. In this case, I'm going to be using water. I said that I'm doing an ester hydrolysis. So the nucleophilic attack will happen here. Notice that when you have, I'm going to do a little parenthesis here. When you form this intermediate oxonium type, this is the carbon right here because of the catalysis with acid. Now, the carbon is more electrophilic because you can do this resonance structure And now notice this has a formal positive. So in other words, the acid catalysis helps by making this carbon more electrophilic. And so more likely to undergo a nucleophilic attack. So that's your nucleophilic attack. After that, you will form, then you need to move those electrons over, so you're going to get OH, OR, which we had at the beginning, and here you will have the nucleophile was water, so you're going to have an extra H here and a formal positive. Because of that, I need a proton transfer step to remove one of these H's. So we're going to have more steps when we have acidic conditions. So the third step is going to be proton transfer. We're going to have a couple of proton transfer steps. First, I'm going to add water as my base. Here, water is the nucleophile. Now, I'm going to use water as base to remove that extra H. And now electrons are going back here. And I'm going to be forming another intermediate that will have OH, OR, OH. And next, to hydrolyze the ester, I need to do another proton transfer to protonate here at the OR. So, H, I'm doing hydronium, right? Remember that we are under acidic conditions. So you're going to get this. And now you're going to have OR, and here is an H, and that's positive charge. So H and OH. We have now the next step. I'm going to have to change the color. Okay. In your next step, that's formal positive, remember, you're going to reform the carbonyl with loss of leaving group to finally obtain the carboxylic acid, but I'm going to have an extra proton, and I need another proton transfer step, and to get that final product will be a carboxylic acid. By the way, this complex mechanism is the reverse of what we call the Fischer esterification, which is from the acid get the ester. So, and all these steps are reversible. So, but point is that always under, what we need to remember is that under basic condition, always that nucleophilic attack is first, and simply form the tetrahedral intermediate, and then reform the carbonyl with loss of leaving group. So 2 steps, easy. But if it is under acidic conditions, we have a number of proton transfer steps. It always starts under acidic conditions with a proton transfer step at the oxygen here of the carbonyl. Then, because you're doing that, the carbon here is more electrophilic, meaning more likely to be attacked by a nucleophile. And what is a weaker nucleophile? For example, this with a negative charge. I did a generic example here. So now you're forming another tetrahedral intermediate. And whenever you have this intermediates in which you have, say, extra proton and a formal positive, you need an extra proton transfer step to have this form. So proton transfer, and then proton transfer here, another proton transfer here. So that is the steps 3 and 4. And then we have the last step is the loss of leaving group, which in this case is an alcohol. Where you're using here, I'm going to say minus ROH. When not here, it is here. You're removing the alcohol and you form the protonated carboxylic acid. So we need a number step. But always remember, you start from here, protonating the oxygen, because that makes the carbon more electrophilic. And you don't need that in the case actually to acid chlorize, in most cases not for the anhydrous. So, but these are the 2 mechanisms that we will be seeing and doing products. So understanding mechanism help us predict products. So that's one reason why we teach mechanisms in organic chemistry.